Arratsaldeon guztioi, niretzat plazer eta ohore handia da benetan Passion for Knowledge jaialdiaren edizio berri honetan parte hartzea eta bereziki iaia donostiar bat gehiago den zientzialari bat aurkezteko egitea. Amandlika sarri etortzen da Donostia International Physics Centerra bizitatzera, bertako ikerlariekin aspalditik lankidetza proiektu ugari egin dituelako. Amandlika lleva décadas trabajando en la física de la materia condensada y en la física de superficies. Obtuvo su doctorado por la Universidad de Lieja, en Bélgica, y posteriormente ha recorrido centros de investigación de todo el mundo, como el Battelle Memorial Institute de Columbus, Ohio, el reputado Centro de Física Teórica de Trieste, en Italia, el European Space Technology Center de Norwich, en Holanda, o los dos principales centros de investigación que tiene IBM en los Estados Unidos, el de Almaden y el de Georgetown Heights, en Nueva York, por mencionar tan solo unos pocos. Desde 1974, Amandlika es profesor en la Universidad de Namur, en su país natal, Bélgica. En 1985, las contribuciones del profesor Lika a la ciencia de superficies le hicieron acreedor al prestigioso premio belga Franqui. Amandlika es un físico teórico que siempre ha prestado una atención especial al contacto con el experimento, con las técnicas y medidas experimentales. Sus contribuciones han sido especialmente importantes en la interpretación de los resultados de distintas microscopías y espectroscopías relacionadas con el estudio de las superficies. Baina zientzialari aparta izateaz gain, Amandlika oso ezaguna da zientziaren historiaren arloan egindako lanagatik. Amandlika ha dedicado mucho tiempo a estudiar lo que él mismo llama scribbles that changed the course of human affairs, los garabatos que cambiaron el curso de la historia. Es decir, aquellas fórmulas y expresiones matemáticas, símbolos, cuyas contribuciones científicas asociadas supusieron una auténtica revolución en la historia, bien por su impacto cultural o tecnológico, o bien por haber aparecido en momentos determinantes de la historia de la humanidad. Estos símbolos y garabatos son los que aparecen en la camiseta oficial de Passion for Knowledge. Asimismo, sus escritos y análisis sobre la historia de la física durante los años de la Segunda Guerra Mundial son una lectura muy recomendable para cualquier persona interesada en esta época crucial de nuestra historia reciente, como yo mismo. Amandlika es un claro ejemplo no solo de la pasión por la física, sino también de la pasión por el conocimiento en todas sus formas. De ahí que en su charla de hoy vaya a combinar física y biología a partir de dos de los conceptos que forman parte habitual de nuestro vocabulario cotidiano, incluso fuera del ámbito científico, como son los rayos X y el ADN. Bestaldetik, Passion for Knowledge-eko lehenengo hitzaldian Niels Bohrren izena agertu zen, eta gaur berriro pertsona bera topatzen dugu, zikloa osatuz nolabait. Professeur Lika, merci beaucoup d'avoir accepté l'invitation à participer au Passion for Knowledge Quantum 13. Et s'il vous plaît, la parole est à vous. The floor is yours, please.
Thank you very much. Should I do something with this? Do you hear me? Yes. Okay. Thanks a lot for the introduction. Much too generous. And thank you very much, Pedro, for your initial invitation. When you sent it to me, I couldn't believe it. What? Me speak at this Passion for Knowledge, at this Festival of Science, knowing the tremendously prestigious people included in the series of speakers. What have I done to you, Pedro? You like me? Well, you may be sure that I like you because I've been coming to the DIPC in the last several years. And whenever I come here, somehow my passion for knowledge is revived, because I find a very good atmosphere at the DIPC, and of course in events such as this, which is not the first one, it must be the fourth or fifth time that I come to this, and it's always wonderful. It's always wonderful to see also that San Sebastian people would care to, stroll and come to this theater just to hear about science. I've never seen that anywhere. It's unbelievable. Congratulations to you. Someday you will reap the benefits of Pedro's tremendous effort. So this is my talk here. Niels Bohr, after all, this is the 100th anniversary of his famous paper, X-rays and the Secret of Life. So we start, like most of the speaker, with this beautiful picture of Niels Bohr, 1913. And however, 1913 was a marvelous year, not only for Bohr's creation of quantum mechanics of the atoms, but because there were several X-ray discoveries just that year, such as the discovery by Max von Laue in Germany that X-rays are waves, electromagnetic waves, capable of being diffracted by atomic lattices. And then the same year, the Braggs, father and son, made a good use of the X-ray diffraction technique to establish the method of X-ray diffraction for structure determination. In this same year, Henry Moseley discovered a rule which is called Moseley displacement rule, and by applying Bohr model to the core level of atoms, he could establish an absolute scale of X-ray wavelengths, which was, of course, necessary in order for the X-ray diffraction technique to be useful. So X-ray diffraction and what is called today X-ray crystallography more generally, plus other physical techniques, NMR and what have you, spectroscopies, plus chemistry, biochemistry, biology, all now are focused on the study of biological material at the atomic and molecular level. This occurs right after 1913, after the discovery of X-ray diffraction. And what was the rush? The rush was to attempt to answer the question, what is life at the molecular level? So concerning Bohr and life, it turns out that Bohr had a funny idea, I would say, not funny, but curious ideas about what is life, in a famous paper that he wrote in a famous conference that he gave in Copenhagen in 1933, and entitled Light and Life. He stated, okay, quantum mechanics has triumphed so far. 1933, it's already 8-9 years that quantum mechanics is having tremendous successes. But as far as life is concerned, it cannot be explained, he said. He said explicitly in this paper, Light and Life, life is to be considered as an irreducible fact that cannot be explained. Just as the quantum of action H is an unexplainable fact at the basis of the stability of atom and molecules. And I would comment just by quoting Bohr himself, about this. It is hard to predict anything, especially the future, because it amounts to say, life cannot be explained. It will never be explained since it cannot be explained. But only 20 years later, that is 60 years ago this year, in 1953, two young gentlemen, Watson and Crick, rushed out of their lab and start running around the street in Cambridge and yelled at everybody, "We have discovered the secret of life." So here is Watson and Crick in front of the first copy of the mechanomodel of the double helix of DNA. What they had discovered is three things. One, they discovered that DNA is in the form of a double helix structure. Two, that the double helices, the two helices are held together by base pairing, A going with T, G going with C, via H bonds. You have heard that already several times in this week, including yesterday by Jean-Marie Lane. And the third thing they discovered was the so-called semi-conservative replication mode of DNA. That is, from one parent DNA double helix, out comes two identical daughter molecules, which are done by semi-conservative replication simply by Watson-Crick base pairing. So these are the three major discoveries. Now, for those of you who have some background in biology or science in general, they should read a wonderful account of the story of the discovery of the DNA structure by Horace Freeland Judson, The Eighth Day of Creation, itself a wonderful title. In my lecture here, I will only speak about the key input of X-ray diffraction to this discovery. So what is X-ray diffraction? Well, it is the scattering of X-rays by atoms and followed by the interferences of scattered waves, since X-rays are electromagnetic waves. And these interferences are collected on a diffraction pattern from which one can be successful to reconstruct the atomic structure of the object. So, schematically, one has incident X-rays falling on an object which scatter the X-rays in all directions, and after scattering, the X-rays interfere because they are waves, and eventually a diffraction pattern is collected on a screen. And here is, to be immediately relevant to the topic of this talk, the early X-ray diffraction pattern of a DNA fiber taken by Maurice Wilkins in 1951. So, X-ray diffraction by a DNA fiber was the method by which Watson and Crick finally got to the structure. What does the technique consist of? Well, here is a DNA fiber. It is a fiber of a fraction of a millimeter, say like a hair, and comprising millions of parallel DNA strands. Dissolved in water and some of the counter ions. And we sent X-ray on this. They scatter, this fiber scatter X-rays, diffract X-ray, and you collect, perpendicular to the X-ray beam, a diffraction pattern. A two-dimensional diffraction pattern on a photographic plate perpendicular to the beam. Okay, let's try to understand this pattern. This is the first, not the first, the second actually, diffraction pattern taken by Rosalind Franklin. It's called in the literature photo 51, because that's the number that this photo had in the dossier. It's a scattering, it's a diffraction pattern of a bDNA fiber in the paracrystal state. Never mind what it means. It means that the fiber has a high water content. So the molecules are rather independent of each other, except that they are parallel. And what you are seeing here is essentially the diffraction picture of a single molecule oriented over all the rotational orientation of the molecule. And the corresponding DNA morphology is this one. It's called bDNA. And Rosalind Franklin also measured or remeasured this picture, which was first taken by Maurice Wilkins, and she had a far better result. And it concerned an aDNA crystal fiber, because some water has been withdrawn from the fiber, and then the DNA has crystallized by touching each other. So it's a crystal fiber, and the corresponding morphology of the DNA double helix is this one here, totally different from this one, although it's a double helix, but the parameters are different. It was a puzzle, how comes the same material could give this or this? Now, I'm going to concentrate on this pattern, forget about this, which can be understood in quite the same method as I will expose, but I won't have time to go into this particular one. So here's Maurice Wilkins, who he called himself the third man of the double helix in his autobiography. He died in 2004. This book, very good, appeared in 2004. And this is a tragic figure of Rosalind Franklin, who took both this picture and another version of this picture. And the fourth man was therefore a woman in the story of the discovery of the structure. And her autobiography is admirably exposed by Brenda Maddox in a book which I recommend to you, which is called The Dark Lady of DNA. Everything is dark concerning Rosalind Franklin. She died when she was 38. She could not take part in the Nobel Prize that was given to the other three men, and so on and so forth. So let me now attempt to explain to you what on earth is the relationship between this abstract picture, the photo 51, and the double helix, such as discovered by Watson and Crick a year later. The relationship could be established in Crick's mind via the theory that he wrote a few months before on the question of how does X-ray scatter from a monoatomic helix. Why was he asking that? Because at that time, Pauling, the famous American chemist, had proposed a helical structure for a protein, which is called the alpha helix. And Crick was doing his PhD on protein, and he invented with other co-authors the theory needed to explain the alpha helix. But, said he in his memoir, I had the theory at my fingertips. So when he saw this picture, he immediately recognized the following elements of structure. You see, if you look at the spots or the streaks, they are all organized along horizontal layer lines. They are called layer lines, which can be numbered 0 for the equator layer line, 1, 2, 3. Somehow there is nothing on the fourth layer line, 5, and then you keep going, 6, 7, 8, 9, 10. Now, this separation between the equidistant layer lines is proportional to the inverse of the period of the helix and can be determined by this measurement of the distance. It's 34 angstrom. The second characteristic is that the spot, as you can see, describe a diamond pattern. And this distance from the center to the north blob, on the 10th layer line, is proportional to the inverse of the distance between the bases or the distance between the nucleotides, that is 3.4 angstrom. Second information that he could read. The third is this spectacular Saint-Andrew cross, in the center of the diffraction picture. And the relevant number here is the opening, the angular opening, 60 degrees of the cross. And from that, Crick could evaluate the helix radius, 1 nanometer. And that was a huge number, because 20 angstrom is a large diameter cylinder, and you can put a lot of things in it, in particular the bases in here. So the next information was this big blob on the south and north, and this manifested the flatness of the horizontal base pairs inside the double helix, and the base pair acted as slits refracting the X-ray waves, and gave rise to these big blobs north and south. And finally, a detail which was not noticed by Crick and Watson was that the force layer line was missing. You see there is a lack of intensity along the force layer line. And this indicates that there are two helices and they are separated by 3/8 of a period. It's hard to believe, but all this is in the diffraction picture, all this information. Sorry. So here is another picture by Maurice Wilkins in 1957. It's a picture of a crystalline fiber of lithium B DNA where manifestly the force layer line is missing, much more beautifully shown. And it can be shown that the missing force layer line is possible only for plectronemic double helix, that is double helix which wind themselves around the same axis, and not paranemic axis, a double helix which are helices winding themselves on two different axes. So here is the double helix. There is a helical strand oriented upwards and another one oriented downwards. The orientation of the strand was evidenced by the A DNA pattern. I won't have time to explain here. And in between, then Watson and Crick in 60 years ago discovered this helical backbone diet, installed H-bonded pairs, A, T, G, and C, and hinted at the semi-conservative mode of replication of the DNA. That was a great discovery, perhaps the greatest in the 20th century. Now, I'm going to show optical simulation of what you have just seen in X-ray, in the X-ray world. What are optical simulation? Well, here is what I have been showing you. X-ray fall on a DNA fiber, diffracted X-ray form an X-ray diffraction picture. In the optical regime, you have a laser, such as this green laser pointer, and you have an optical diffraction grating, which is this slide here. And I'm going to pass the laser through the different gratings and produce optical diffraction pictures of which you will see how to reconstruct the whole picture in X-ray by doing the diffraction here in the optical regime. It's interesting to note that the optical light is 3 or 4 or 5 orders of magnitude smaller than the X-rays in wavelength. So the green laser that I use here is here the red laser that you are going to see, the result of which you are going to see in the next few pictures, are both visible light, which are all squeezed in this very narrow area here, 10,000 times larger X-ray wavelength than the X-rays. So here is the diffraction slide, and in order to make the diffraction demonstration, I'm going to need a volunteer from the audience. Does anybody wants to help me doing the diffraction? Because, okay, before I accept any volunteer, I have to request someone who has some laboratory experience. Do you have a laboratory experience? Probably not sufficient. Anybody else? Oh, there is a hand going up here, but this is Professor Hirschbach. Professor Herschbach is going to help me doing the experiment. So you push on this button here for the slide, and you have the slides here.
That looks like I'm capable of pushing the button.
Yeah, be careful not to break your leg.
Well, in the theater, they say you should break your leg.
So if Professor Herschbach, you can move all the way up if you wish. Yes, because the farther you are, the better. But there you are. It's okay there. You can stop there. And now let's go through the demonstration. I just gave to Professor Herschbach, can you believe me? I have been invited to give a lecture to the symposium on passion for knowledge, and now I have an assistant who is a Nobel Laureate. I think my grandson are going to be thrilled. Anyway, I have this diffraction grating. There are 9 gratings, and you can see each grating has a diffraction motif. So it's as if it was the molecule, but as if it was. You don't need to show it now. I will call you, okay? So let me just comment a few things about what is in the slide. You have a diffraction motif every time, like a molecule, and by the time we are at the nice grating, then I'll have the full DNA picture there. So let me see what. So I'm going to go from grating 1 to grating 9, and this is a travel across time from 1803, where Thomas Young demonstrated the wave nature of light, to 1953, where Watson and Crick discovered what is light. So the first diffraction grating asked the question and replied to the question, what is light? So now, Professor Herschbach, can you show us the diffraction pattern of this motif? So this is a set of slits, equidistant, and the diffraction pattern of that with a green laser is this fantastic picture. Thank you. Now, if I can find the proper button here thank you for the light. So what we just showed is the grating number 1 has n slits. Instead of having 2 slits like Thomas Young would use in 1803, you have n slits, and the experiment works better this way. Of course, he didn't have a laser, but he managed to create coherent light, and he managed to demonstrate the following properties. That is the layer lines, so everything is organized along the layer lines. Equidistant layer lines, and the distance between the layer lines is inversely proportional to the distance between the slit. And this is the way Thomas Young demonstrated that visible light is a wave. Now, the next one is a set of slits again, but they are inclined to the right. And Professor Herschbach is going now to shine the light through the second, which is this. That's the first, this is the second. And as you can see, the line of maxima is now perpendicular to the I think Professor Herschbach has trouble finding. There it is. A little bit on the right, please. You are not quite on the second grating. There you are. You see, you have. Thank you very much. And while you are looking for the third, let me show you what you just saw. This is what I call a Zig grating, and the diffraction pattern of that is this. You've seen it in green, here it is in red. So the period here appears as the inverse of the distance between the layer lines, and the direction of the maxima is perpendicular to the Zig. So now the next one is obvious. Of course, you have a Zag grating, and Professor Herschbach is going to show on the third to the right diffraction pattern, and there you are. There you are, magnificent. So, do you see it, by the way, in the audience? Yes? Is that clear? When Professor Herschbach managed to hit, there it is. Okay, it's probably overlapping two of those, but it's not. Okay, so here is what is seen. So the Zag grating gives layer lines again and a line of maximum which is perpendicular to the slit orientation. And then, of course, if you put the two together, then you have a zigzag grating. And here is a motif, and this is the result. Have a beautiful cross. A beautiful cross, thank you very much. I don't know what happened, but it gets blurred. And anyway, this is a result with a red laser. And you have a zigzag, you have a period, and the period determines the inverse of the distance between the layer lines, and the angles between the arms of the Sintern-Roux cross is equal to the angle between the zig and the zag, and therefore you can rework out all the geometrical parameters of the zigzag from the diffraction pattern. The next one, which is the fifth one, is another zigzag. Another zigzag, but with a smaller period, sorry. And there it is. You have a marvelous diffraction pattern with a Sintern-Roux cross and a smaller angle between the arms of the cross. Thank you very much. So here we are again. The arms of the cross are perpendicular to the zig and the zag. Okay, now the next one, it is a 6. It's a very important diffraction grating because it's a sine wave, continuous sine wave. And again, you have a Sintern-Roux cross. And a sine wave is very important, thank you, because a sine wave is a helix projection in a plane of its axis. So we are coming close to the DNA in this way, and the arms of the cross of the Sintern-Roux cross makes an angle phi, which allows you to work out the radius of the sine. The next one is a double helix. You see there are two helixes in the motif, two helices, and they are separated by 3p/8. Professor Herschbach is looking for this, but he can find it. So let me try to show it to you from here. Oh, this is not this one. Okay. Oh, there you are. You see, you have again a Sintern-Roux cross, but you have two beautiful black line here, which is the fifth layer line is missing. And that's because there are two sine waves and they destroy each other along the fifth layer line. Thank you. So this is it here, seen in red. You see the period appears as the inverse of the layer lines. And you have two helices separated by 3p/8, and they produce extinction on the -4 and +4 layer lines. The one before last is a sine wave again, but it is atomized this time. And Professor Herschbach is going to look at the... And you see you have layer lines, you have a cross in the middle, a Sintern-Roux cross. Now you have a diamond pattern. And the diagonal here, the inverse of this gives you the distance, axial distance between the atoms. Thank you. You got it this time, Professor Herschbach. Beautiful. And the last one, so I'm sorry. So this is the result in red, less visible than in green. And the last one, so the distance between the layer lines gives the period. And the distance between the nucleotides is given by the diagonal of the diamond pattern. The last one is what is life. And this is a double helix, atomized, and you see everything is in here. You have layer lines, a central cross, a diamond pattern, and a missing fourth layer line, which is not very visible, but never mind. Okay, so if someone can help Professor Herzbach to his seat. I would like to thank Professor Herzbach for this little game that we played. He was the only one to know about it. I'm very grateful to you, Dudley. And the whole organization crowd here is very grateful to you for not only for this, but for having given a fantastic first talk opening this thing, but for the tremendous courtesy you and Georgina are doing to the organizer to stay up to the end. And I would like a round of applause for Professor Herzbach. So the last picture we saw is just a synthesis of everything we have seen in the demonstration. So this is the diffraction picture produced optically. That's a real X-ray picture. It's obvious that the two are very similar. Thank you very much. I have only very limited time, so I'm not going to review all this and spend 2 or 3 minutes on the last few thoughts of Bohr. Bohr, famous paper in 1933, Light and Life, has in fact 3 main ideas, if you read it between the lines, so to speak. The first one is rather weird. Life and death, he said, are complementary. But he meant, you know, he didn't mean just complementary in the linguistic sense. He meant similar to X and P, position and momentum in quantum mechanics, or a creation and destruction operator in quantum field theory. And in order to justify this weird assessment, he said in the paper, to study a living organism, you need to kill it, which is unbelievable for a thinker of this status, of this caliber. Anyway, that's what he said. And to this I will add Feynman's warning, the easiest person to fool is oneself. The second idea was the one I just have already told you about. Life cannot be explained. And I don't mean just more complex. It cannot be explained, he said. And the third idea was life requires new laws, compatible with but beyond those of physics and chemistry, and not just more complex, but nor emerging behavior, but new laws. Shall we detect a trace of animism or vitalism in this statement? Some people have said yes, there is some trace of animism. But an important fact is that Max Delbrück was in the audience, a physicist in 1933, a brilliant young physicist who decided to quit physics because of these ideas, in order to search for those new laws. And what did he do? He created the bacteriophage group at Caltech and spent the rest of his life doing phage biology, phage genetic. And in 1976, this is what he said in an article that he himself entitled Light and Life, number 3, because there was a number 2 in between, but never mind. And this is what he says in this article. The double helix indeed, with one blow, the mystery of gene replication was revealed as a ludicrously simple trick, making those who had expected a deep solution feel silly. well, not so silly, since he got the Nobel Prize in Medicine in 1969 for his contribution to bacterial genetics. Here's what says, well, I should perhaps skip this and say what, and show you what another luminary of molecular biology said, and that is Gunther Stent. He wrote an article in Science in April 1968 entitled Light and Life, Niels Bohr Legacy to Contemporary Biology. Here's Gunther Stent at an advanced age. And he wrote there, no new laws had turned up. Making and breaking hydrogen bonds seems to be all there is to the working of the hereditary substance. And I will add to this that there is indeed plenty of complementarity going on in life, such as base pairing by hydrogen bonds, but so far, at least, no complementary of the kind envisaged by Bohr has been discovered in biology or anywhere else. So let me present you the last picture, a few words about the hydrogen secrets of the 20th century, I would call it. There was a discovery of the nucleus in 1911 by Rutherford, which was used by Niels Bohr in 1913 to create his atomic quantum atom. And then a few years later, Linus Pauling developed the concept of age bonding, with which he demonstrated the stability of the alpha helix and the beta sheet of protein, as well as the structure of water, in which all these biological molecules are dissolved. And, the last piece was what I just told you, that is the discovery of the role of age bonding by Watson and Crick in The Secret of Life. I left a gap there for those of you who have knowledge of the 20th century science history. What is missing? Another hydrogen secret is missing in 1952, and this is the secret of death. That is the discovery by Ulam and Teller of a mechanism to make an H bomb, not an H bond. Now, I am amazed because yesterday I was interviewed for a full hour by a brilliant journalist of El Diario Vasco. And this morning, lo and behold, there is a paper on page 5, I think a full page, on what I said. And there is a very nice summary of the interview. Here is a title, however, for which I have some objection. He says that I said, la curiosidad y la pasión por la ciencia pueden cegar al científico. He means that I am blind. But blind to what? Blind to the future? Everyone is blind to the future. And remember what Bohr said, it is hard to predict anything, especially the future. So I don't see how I could be ciego for the future, since nobody knows what the future will be. Anyway, ¿hay límites éticos para la curiosidad? He asked me. And I replied, como no sabemos todas las consecuencias que pueden tener nuestra investigación, no podemos poner los límites éticos. And he asked me, ¿cómo se quita el miedo a la ciencia? Con educación. Eso es lo que el DIPC intentó hacer en San Sebastián. And with this, muchas gracias.